Okay, so this video is going to look at metal extraction from the AQA AS chemistry specification. What it's not going to cover, it's not going to look at the environmental aspects, so nothing to do with recycling. It's not going to look at the scrap iron part. It's just going to look at the actual extraction of metals themselves. So looking at iron, manganese, copper, tungsten, titanium, and aluminium. Right, so metal extraction. Well, there's metals invariably come from the ground. And one way of extracting metals would be if you've got something like gold, for example, where it's very unreactive, and that can just going to be mined as a gold vein. The way the AS specification looks at the metal extraction is looking at the idea of ores. So an ore being essentially kind of like, if you think about it, like a rock that contains metal. And there's a specific thing for it to be actually labelled as an ore and not just a rock that contains metal. Specifically becoming an ore, the amount of metal must be viable. And what I mean by that is if it's a really low grade ore and it contains a tiny amount of metal, then the extraction process would probably outweigh the cost you would get from the metal itself. In that case, you probably wouldn't class that as an ore, or you'd class it as a low grade ore. It wouldn't be used in these kind of processes that are going to be looked at in this video. We're talking about ores where it is viable, it's economically viable to actually extract the metal from it, because the cost of the metal will outweigh the cost of the extraction process. Okay, so these ores exist as oxides, so metal oxides or metal sulfides. So they fall into those two categories, metal oxides or metal sulfides. The metal oxides we'll come on to in a minute. Start with metal sulfides, because that's the easiest part. If we've got a metal sulfide, regardless of what the metal is, and I'm going to do a generic M for my metal, so there's my metal sulfide, generic metal here. I go through a process called roasting, and what that is that you react it with oxygen. And the process of this actually creates an oxide. So really we're looking at reactions. The extraction of the metals is from the oxide itself, not from the sulfide. So we're turning the sulfide into an oxide. And we're going to do that by reacting with oxygen. That's going to create us our MO, so our generic metal oxide, plus sulfur dioxide. And that also needs balancing up. So 2 there, 3 here, 2 here. 2 there. A couple of points then. Well, one point mainly. This thing here, we'll go a different colour on that. This thing, sulfur dioxide, as soon as you see that, you should be thinking acid rain. And of course, covered, I believe it's in Unit 1, acid rain is a problem. Acid rain causes damage to crops, to forests, to lakes, all the rest of it. That's a problem. So that is an environmental issue with the roasting of a sulfide to form the oxide, is that you are going to produce this sulfur compound here because of the sulfur present being oxidized here, being reacted with the oxygen to form sulfur dioxide. But skipping this, leaving that sort of aside, we've got our metal oxide. Now the first two I'm going to look at is our iron oxide and manganese oxide. So iron 3 oxide it is on this one, and manganese 4 oxide. Now these numbers are the oxidation states of the particular metal. So I know that in the case of the iron, I've got this iron 3 plus ion, and in the case of the manganese, I've got a manganese 4 plus. So I've got a manganese with the 4 oxidation state and a 3 over here. Now what's quite nice about these two is two separate metals. They follow very similar extraction processes. Starting with the iron oxide then. So iron oxide is Fe2O3. You must learn all of this, including all the equations as symbols. It must be done. So I'll write this balanced out, so, and then I'll explain this in a second. Okay, so my first way of extracting iron from the iron oxide is a direct reaction with this thing here, carbon, which is in the form of coke. And this is something you may have done at GCSE actually, the extraction of iron from iron oxide using coke in the blast furnace thing, which looks something like that, and you've got a couple of sort of tubes to remove impurities, and then iron and all the rest of it, and it's hot in here, and yeah, no, stuff goes in the top, blah 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 blah. So iron oxide reacts with the carbon to produce iron and carbon dioxide. So what we've got here is we've actually got a redox reaction going on. We've got reduction of the iron oxide. So the carbon equals reducing agent. The carbon is reducing the iron oxide, and in the process the carbon is oxidized. So we've got oxidation occurring here. Let's change the color of that. Oxidation occurring here, and we've got reduction occurring here. And we can go one further and we can say, well, what are our oxidation states in these various points? And we can say, well, we already know iron is +3, element on its own, it's going down to 0, so it has been reduced. The carbon starts at 0 and ends at +4, so here it has been oxidized, as we would expect. So we've got a redox equation there. Now I'm not going to do that with every single one, but certainly if you've looked through the redox topic and maybe you've watched the video on the redox topic as well, you should understand how to find out oxidation numbers of various things and apply them to given situations. And of course the idea of the reduction of the oxide here, and also in the manganese oxide, that's a very important point. You must know that. And the second thing we can do here is we can still use our iron oxide, but we can actually react it with carbon monoxide, again producing iron and again producing carbon dioxide. Balancing this up, 3 here, 2 and 3, that should balance nicely. Okay, so what you actually find is that the carbon within the blast furnace can be turned to carbon monoxide, which itself can act as a reducing agent. And you can see here, this again is oxidized, the iron oxide is reduced as before, which I think is reasonably straightforward. In terms of conditions, because you are expected to know the conditions, this occurs at 700 degrees Celsius. Other side here, manganese 4 oxide, it's exactly the same, but obviously with manganese rather than with iron. We have MnO2 reacting with carbon to give us Mn, manganese, plus carbon dioxide. And then down here, exactly like the other example, we have the carbon monoxide coming in, giving us manganese and carbon dioxide again. So balancing these up, first one is balanced, second one, a couple of 2's here. As I've said, you must know these equations including balancing. What they quite like to do, and I think it was a couple of years ago, I forget the exact year, there was a question on metal extraction where they'd used a complete, I think it was molybdenum or something like that. They'd used a completely random element, but it was in terms of using your understanding of metal extraction and applying that to this new situation of molybdenum. I think it was molybdenum, instead of using the classic sort of iron or manganese or whatever else. Okay, this one occurs high temperature here. High temperature needed for this reaction, 1200 degrees Celsius, and that pretty much is iron oxide and manganese oxide reduction. And if you can do one, you can do the other. They're quite straightforward, which is quite nice. So, go and have a look at copper now. So iron oxide, manganese oxide. Now copper actually a little bit different. The copper is extracted from its ore, which actually is primarily copper carbonate, and it's a copper ore called malachite. You don't need to know the names of these ores. I mean, just to go back up here, this is primarily hematite, and this I believe is pyrolusite. It doesn't matter the name of the ores. You might be given it in a question. They might say to you, an ore of iron, hematite, Fe2O3, blah blah, an ore of manganese, pyrolusite, MnO2, they would give you the information required. They might throw names and all the rest, but they will give you the chemical information that you need. Okay, so copper ore, mostly, which is malachite, and this is actually now copper carbonate, which means we've got a slightly different way of doing things. There are two methods. First is direct reaction of the copper carbonate with carbon to give us copper and carbon dioxide. And we'll balance this up now. So balancing this up, we need a 2 here, 2 here, and I believe we've got a 3 there, and that's fine. That's the first method then. So the reaction of the carbonate with the carbon. Again, we can look at reduction, oxidation within this. The second method is a slightly different one. We can thermally decompose the sorry, I'm trying to spell that. We can thermally decompose the carbonate down into copper oxide and carbon dioxide, and we can then react the copper oxide with carbon to give us the copper again. So a couple of methods here. Again, learn them. There's just a lot of equations here and a lot of learning, and obviously, as I said, be aware of application. But you've just got to know a lot of these equations, which is kind of sucks a little bit, but there you go. Once you actually sort of think about what's happening, it kind of makes sense though. It's not too much there, and a lot of carbon involved as well. Okay, have a look at tungsten now then. So, tungsten. This is where things start to change. We don't use carbon for this one. The reason is that tungsten carbide, which is an impurity that can arise basically from using carbon, you can form this tungsten carbide. But the thing is, it's brittle, and that's not very useful, particularly when tungsten's such a hard metal. We don't want that brittle nature in there at all. So what we can use instead is we use hydrogen. So our tungsten oxide, WO3, is reacted with hydrogen, 3 H2s, to again produces the metal, and in this case water. And again, we can look at it in terms of reduction and oxidation. And if you forget what the other product's going to be here, when we know we're always going to form the metal, the other one's going to be the oxidized form of our reducing agent. So in this case, hydrogen, we add an oxygen to it, we're going to get water. Carbon, we add an oxygen to it, or 2 oxygens as it would be, we're going to produce carbon dioxide. This one occurs about 700 degrees Celsius. A couple of things to be aware of here, particularly this is more expensive compared to carbon anyway. It's certainly more expensive than carbon. Carbon's very readily available, particularly in that form of coke. It's very, very readily available. The other thing is it's explosive. We're talking 700 degrees, hydrogen mixed with oxygen. We're going to have a bit of bang there. So they would obviously need to take care that maybe there's no oxygen present. If there's no oxygen present, then there's no risk of combustion there and explosion. So there's your tungsten. Again, another one to learn. This time, paying attention to the fact that we've got hydrogen, not carbon, and that's the key thing there. 2 more left. We've got to look at aluminium and then titanium. Now, aluminium's one that I'll go across for this one. Aluminium's one that you will have probably looked at GCSE. So aluminium from bauxite. Again, an oxide here, aluminium oxide, Al2O3. Now, a starting point here. This is extracted using electrolysis. So we use electrolysis. Now, when we're electrolyzing something, we can't have it as a solid. It needs to be molten or as a solution. So to melt this requires about 2000 degrees Celsius. Now that's fairly high, and that's considering how high that temperature is, and then considering the fact that electrolysis itself is an expensive process because of the huge amount of current that's required, and the huge amount of electricity that's required. One plant, I think in Australia, uses as much electricity as a small town, so there's a huge requirement for electricity. This is only adding to the cost. So what's done instead is this mineral called cryolite is used. Now cryolite is as far as I'm aware, is a naturally occurring aluminium containing mineral. And what they do is they melt the cryolite, and that melts at around about 900 degrees Celsius, which is clearly much lower. What's quite good then is that with the molten cryolite, we actually dissolve the aluminium oxide in it. So the aluminium oxide is dissolved in the cryolite, which means we split to our two ions. We get the aluminium 3+ ion, and we get the O2- ion, which is exactly what we want, and then we can carry out our usual electrolysis. Now the setup of the electrolysis used is kind of like this. We have an outer casing of some sort, nice straight lines. In there we have a lining of carbon, which actually acts as the cathode. Straight lines, oh dear. So negatively charged carbon cathode to the negative electrode here, and then what we do is in the top we stick a couple of positive electrodes. So coming around here, there we go, nice positive charge going in there. So we've got a negative cathode here, negative electrode of the cathode, and we've got the positive anodes here, also made of carbon, and obviously that's also the same. In here we have our cryolite and aluminium oxide. What we find is as we carry this out, we get molten aluminium. Because of the temperature, I think aluminium melts perhaps around like 700 degrees. This temperature here is high enough that actually it melts the aluminium. It falls to the bottom, and what happens is it can be pumped off. So we can remove our aluminium to here. Now, what happens in order for us to form the aluminium? Well, aluminium is going to be attracted, the aluminium ion is going to be attracted to this outer, or this lining, this cathode, this negative lining. So we're going to find the aluminium, the Al3+ ion, is going to be attracted to that, and it is going to be reduced. And I know it's reduced because it's gaining electrons. So reduction here, remember, oil rig. So it's gaining electrons and it's becoming aluminium. The other hand here, we've got the oxide ion. That's going to be attracted to these guys, to these carbon anodes. The oxide ion gets attracted and it's turned to oxygen. So let's double that up. And this is, of course, oxidation occurring here. So we've got our redox occurring. So reduction of the aluminium, oxidation of the oxide ion. What you then find can happen is this oxygen, because of the high temperature used, the oxygen will react with these carbon anodes and it will form CO2. That means these ultimately are going to wear away, and so they need to be replaced every now and again because they will wear away because they reacted with the oxygen and therefore forming carbon dioxide and thus getting smaller. Okay, and that's really everything about aluminium. So bauxite, not melted, dissolved in molten cryolite about 900 degrees. It's electrolyzed. We have a couple of half equations going on here: aluminium ion reduction, oxide ion oxidation, and then a further reaction of the oxygen with the carbon. Okay, final one. That leads us on to our final method of extraction then, and that is of titanium. So titanium. Now, titanium comes from an ore called rutile, which I think is probably my favourite ore. If I had to choose one, it'd definitely be rutile, which is a form of titanium oxide. It's titanium 4 oxide. So as an oxidation state of 4, should be a capital there, I apologise. As an oxidation state of 4. Now this one's again extracted in a little bit of a funny way. I don't want to say we don't use carbon, because we do, but we don't use carbon alone. If we used carbon alone, we would produce this titanium carbide. Titanium carbide is, again, brittle, not good. Titanium has a lot of uses, a lot of medical uses. It's used in hip replacements, it's used in rods to strengthen bones and all the rest. We don't want it to be brittle. We're putting a brittle titanium rod into someone's leg, we could have a real problem there. So we need good, strong, pure titanium, or we can alloy it later on if we wish, or anything like that. It has a high strength to weight ratio as well, so it's a really, really good metal. So we don't use carbon alone. What we use instead is we react our titanium oxide with carbon, but also with chlorine. So it's reacted with carbon in a stream of chlorine, and what that allows to happen is we again form a titanium, but not pure titanium this time. There's a few steps here. We form titanium tetrachloride and then some carbon monoxide. So now to balance the rest of this up, there we go, it should be fine. At this point, I should say that the whole process of titanium extraction is a batch process. Now, titanium is, it could be like a wonder metal. It's brilliant. It's very resistant to corrosion, very strong, fairly light, all the rest of it. Problem is, it's very expensive to produce, and the nature of the process of its extraction means that it's expensive. So it isn't necessarily used as much as it could be if it were much cheaper to extract. Okay, this happens at about 900 degrees Celsius, and then we have another step now. We are now going to deal with the titanium tetrachloride. In between these steps, to make sure we've got good pure titanium tetrachloride, the titanium tetrachloride is purified, and that's done using fractional distillation in an argon atmosphere. So we do titanium tetrachloride purification using fractional distillation in an argon atmosphere, and then we go to our final step. Now there are two options here. You can react the titanium tetrachloride with sodium, or you can react it with magnesium. And this tends to depend on really sort of, for what I've read, where in the world you are. There's options, and again, this is going to add to the cost to reasonably expensive metals to extract this titanium from there. So we end up with titanium in both cases, and then we end up with sodium chloride, or we end up with magnesium chloride, and with a bit of balancing on that, that should do it. There you have it. That's the titanium. So we again, looking at the various points here, we've got reduction of the titanium from its +4 state here down to 0 using either the sodium or the magnesium. Either does the same job. That is a fairly sort of whistle-stop tour of the extraction of metals, but really the problem with this topic is there's just a lot of learning, making sure you know all of the little details, including all of these equations. If you know all them, then you can of course answer a question which asks you about those particular metals, but you can also apply that knowledge to other metals which they say might behave like certain metals. So I hope that's been of help. If you've got any problems or any feedback at all, by all means leave it in the comments below. And there you go.